How you doing, folks? I'm Mr. Rose, and today I come to you with a very serious problem. And that problem is many people have been asking me about question 25.10, which you can see right here. So I would like you to take a moment and read that while I set up and we can really take on this very serious question. All right, so now this is, like I said, a very serious matter because we've already answered some of these questions before. So hopefully you're asking yourself, why would we be discussing some of these questions again? And that's just so we know that you understand what's going on. And so you can even check me and make sure I know what's going on. Because let's face it, half the time, I don't really know what's going on. So the first part of this question talks about the current and or the drift speed on either side of a resistor. So if I just draw part of a circuit, I don't really care. Put a little junction point there. Put a resistor there. Put a little junction point there. Let's define some current. That stopped working. Let's define some current. I traveling in that direction. All right? So now we've got all these nice definitions. We have what's going on. Well, if I still have this thing set up in series, again, we kind of talked about this before with a big wire and a small wire. This resistor, I could just say kind of acts as a small wire. But the resistor is just there as an intermediate. It is an intermediate to our series circuit. If this wire and that wire are identical, I don't really care about anything that's happening here. If those two have the same diameter, if those two are the same wire, if they're the same material, the same resistivity, the same conductivity, all in series, well, I know the current is the same, I know the cross-sectional area is the same, I know the conductivity is the same, which means everything about the wire there and there are identical, including the amount of current, the electromotive force, the voltage, and the drift speed. We don't talk about what's happening at the resistor, so we don't care. But if I wanted to, we could talk about that like we have earlier. The resistor is resisting electrical current, but it's got the same value, the same I value, so we'd be able to figure out what happened to the drift speed there. Now, the second part of the question is really where I want to discuss. The second part of the question talks about potential energy. What is the potential energy of the charge carriers or the electrons? Let's label this now A and B. So essentially, I want to know where is there more potential energy per unit charge, at A or at B? Well, if I just described everything is the same, current is the same, voltage is the, oh, I'm sorry, I don't want to say voltage. Current is the same, drift velocity is the same, conductivity, resistivity, all that is the same. Maybe I'm thinking to myself, potential energy must be the same. Those guys are moving at the same speed, V and V. But we're thinking mechanics, not electricity and magnetism. Recall our potential energy. Potential energy is the charge, Q, times the electric potential, or V. Now, if I have current traveling from one side to the other side, we know current is going to go from a high potential to a low potential. A higher V value to a lower V value, which I can measure the potential difference, VA minus VB, to get that potential difference. So since my current is flowing from a higher potential to a lower potential, I would have to know that VA is bigger than VB. Well, if VA is bigger than VB, then just based on definition, my potential energy at A is bigger than my potential energy at B, which means as charge carriers traverse a circuit, if they are going from a high potential to a low potential, language is very important here. As they travel from a higher potential to a lower electric potential, they would have less and less and less potential energy. So the potential energy here per charge carrier would be bigger than here. And if this wasn't a resistor, if this is a light bulb, you'd be able to see that because light bulbs light up. That is energy per unit charge, or energy per unit time rather, which is power, which means we would see that it is dissipating and or using some of that energy. So That's all I really have for you. It's kind of a counterintuitive question. Current is the same. The electromotive force or the electric potential difference is different because we're going from a high potential to a low potential. And again, that potential relates to that electric potential energy. I hope this really charged you guys up. And that's all I have. If you're watching this on my YouTube channel, again, feel free to like, comment, or subscribe. Feel free to send some questions forward. Maybe some other people will even answer them on the YouTube channel. And that's all we have for you. I need credits or something like that. We need to have like maybe a fade out music or something. Like Bill Nye has Bill Nye the Science Guy at the end. I don't have any of that. One day. Anyhow, again, that's really all I have for you. And you'll see me next time.